Hi everybody. Today we are going to do a short lecture on an overview of Chapter 4. Chapter 4 in your textbook talks about work. And some of the things that I would like to talk about as we discuss the ideas of Chapter 4 is what work is and what work isn't, and relate that to other forms of energy. So having said that, I'm going to come over here to the document cam, and we will talk a little bit about the idea of work. Oops, that's not going to do. Let's get this. There we go. Work, heat, internal energy. Ugh, this is a bad pen. I don't like it. Potential energy, and kinetic energy, and then other forms of energy like electrical energy and so forth. But these are referred to as mechanical energy. So all of these quantities, work, heat, internal energy, potential energy, and kinetic energy, all have the same dimensions. And it all goes back to an integral of del W is equal to FdR, or that work is a force acting through some distance. So the dimensions of work, if we do that integration, would be a force times a distance, which is a length. So that would be foot-pounds, inch-pounds, etc., Newton meters, and Newton meter has its own unit, which is a joule. All right. Now, heat and work by convention in the U.S. customary system may have different units. For example, work tends to be measured in foot-pounds, and heat tends to be measured in BTUs, or British thermal units. But dimensionally, they are the same. They're still a force times a distance. Okay. Now, the big thing about the first law of thermodynamics, which is what we're really talking about here in Chapter 4, is that energy is conserved. Okay? And this is factually correct, and it's a basic law of the universe. It does not, it applies in a different way if we blow up atoms, if we do nuclear reactions. But we're not talking about doing that in mechanical work. If we have a nuclear reaction, Einstein tells us, and it bears out truth, that energy is equal mass multiplied by the speed of light squared. And this has a lot of consequences. This is a really interesting but deceptively simple equation. C is the speed of light, which is a huge number. You square it, it's an extraordinarily huge number. So what that means is you've got a lot of energy for blowing up a tiny bit of mass. It also tells us that to move a little bit of mass close to the speed of light, we need an incredible amount of energy, which is why, and it also indicates that maybe the mass increases as we move it toward the speed of light. So there's some asymptotic theoretical limits that we may not be able to pass. Actually, it looks pretty clear that we're not going to be able to pass. But there's a lot of consequences. But in terms of energy, what it means is a wee tiny bit of mass that is deconstructed at the atomic level will result in a huge amount of energy. But this doesn't have an application for, dropping a bucket of water off a cliff. We're not getting, or moving a car at 90 miles an hour. Those things, we're not talking about anything having to do with relativity at that point. So anyway, work, heat, internal energy, potential energy, kinetic energy, and other forms of energy are all conserved. Now, work and heat are not let's say they are path functions, meaning how much work you get and how much heat you get from an exchange of energy depends on how you get from point A to point B. So we describe that as being work is an inexact differential. Work is an, let's say del work is an inexact differential. Okay, but it turns out, and your authors developed this pretty well, is that the difference between heat and work is not inexact. It's equal to the change in energy of the system. Now this is for a closed system. It's all, we'll talk about open systems in chapter 5. Open means that there's mass coming in and out. Closed system means there's no mass coming in and out. So that means that energy only leaves the system or enters the system based on either heat or work. But so we're basically talking about no mass enters or leaves the system. All right. So work minus heat, we have to keep our signs straight on this issue because it can be interesting. Work looks like this. The integral of f dot dr. Okay, so let's do a typical kind of a thermodynamic problem where we find work is raising of a piston. So if you have a cylinder fitted with a piston and inside you have some gas or liquid and you add heat to that cylinder, the piston is going to go up, right? And that is a delta y or delta z, depending on what your axes look like. Okay. Now, since the gas itself, the cylinder that the gas or liquid is contained in, doesn't change shape, if we take a look at this, we can also say, well, dr, let's just say delta y times the area of that piston, delta y times the area of that piston is going to equal the change in volume because there's no change in area at all. That means that delta y is equal to the change in volume over the area of the piston. Okay, well, if you consider that, then in this particular case, work is equal to F times, if everything's constant, I'm making a lot of math assumptions here, but the change in volume over the area, or I can rewrite that as force over area times delta V, and force over area is pressure times delta V. And it turns out this form of the equation is extraordinarily useful for expanding gas. Okay, so the work done by raising a piston in a cylinder without changing the area is equivalent to the pressure of the gas times the change in volume. Now that assumes I did some stuff with the integral here. I've built in an assumption that P is constant. And for an expanding gas, it usually is, unless there's stops or a spring or something else on the piston. The piston will just raise and fall with the pressure of the gas. Okay, it's a very classical thermodynamic problem. All right, so if you take something like this, what kind of energy, except for work and heat, might be involved? Well, that delta E term could involve a change in internal energy. It could involve a change in potential energy, and it could involve a change in kinetic energy. Although it's unlikely, right? If we just are heating up a gas, the only thing we're really changing is the internal energy. The kinetic energy and the potential energy would only change if we dropped it off a cliff or if we put it on a cart and accelerated it or did something funky with it like that. But if it's sitting still, very often these equations will reduce to this. So if you look at this equation, pressure is always positive. Absolute pressure is never less than 0. So work is positive if delta V is positive. That means if the volume of this cylinder piston increases, if the volume of the gas in the cylinder increases, then the work is positive. So an expansion of a gas is positive, and a compression of a gas is negative. All right, what about heat? Heat going in is positive, heat going out is negative. And once in a while in a chemistry book, you'll see this equation written with a different sign convention. You have to redefine positive and negative heat. But in our textbook, and it's standard for engineering, this works. Okay? Now, internal energy is something you would find in the tables. And you remember in the tables, in the steam tables, we have little u tabulated. So this is big U2 minus big U1 from one state to other. Little u is tabulated. Big U would be mass times little u. So to simplify this again, we could say W minus Q is equal to delta U, which is equal to mass, because we're not changing mass, times little u2 minus little u1. And that is the form of the first law of thermodynamics for a closed system involving the expansion of a gas. And that's like one of the most classical formulas. This type of work is called boundary work. Okay? Now, there are some other problems where you have different types of processes, and work will be a little bit different, because the integral work always goes back to this integral of F dot dr, or for gas expansions, P dot dv. Okay? So you can see here that if P is constant, it comes outside of the integral, and then it's just P times delta V. If P is not constant, we have other processes that we need to take into account. So they discuss, everybody's favorite, the isochoric, which is also called isovolumetric. That means the volume stays the same. You'll never get one of these on the test, by the way. But if the volume stays the same, what is delta V? Nothing. So what's your work? Nothing. That's right. Work, boundary work equals 0.
One of those on the test.
It's like everybody's dream problem, I think. So for isobaric, work is equal to P times the integral of delta v, dV, which is this. Okay. There are two other processes that they talk about in your textbook. One is isothermal, which, once again, there's a common misconception. I just want to clear up. Isothermal does not mean Q is equal to 0. Okay? You can have a heat transfer isothermally. It happens all the time. It's weird, but it's true. But you have to be careful to separate those two terms. If Q is equal to 0, it's called an adiabatic process. That's the perfect thermos, right? You have a thermos, you got hot coffee, you leave it there for 5 years, you come back, it's exactly the same. That is an adiabatic process. The area around the thermos never lost any heat or gained any heat. Yes?
Can I see a little bit of notes behind
About which?
I wasn't able to.
The page before.
Oh, sure, absolutely.
How does the units work out with the like P delta V? Because the pressure would be like PSI, right?
Yes.
The volume would be like cubic inches.
Isn't that lovely?
Or something.
Right.
So would the 2 inches cancel and be like
Yep.
pounds, inches, pounds?
If you have this, right, PSI per inches, this is a pound force per inch squared. Inch to the third. Cancel, inch pounds, right? If this was in PSI and this was in cubic feet, yeah, so then you would go pounds per inch squared times feet cubed. Then you would have to do something like 12 inches per foot, cube both. And then you get rid of the feet cubed, but you have to multiply by 12 by 12 by 12 to get it into inch pounds, yeah. Good question. See, it's a good practical question. All right. So the processes that I wanted to make sure that you had seen before we finish up this little lecture today, we talked about I need to get some more paper. Should we talk about that? I'm so poor, I don't have enough paper to write on my document, Cam. Not really. So for a closed system, expansion of gas, W minus Q equals delta E. Work, we have isobaric, and that becomes P delta V for a gas expansion. Isochoric, which is 0. These are backward. I'm sorry, I should put my W on the left, but there you go. We have isothermal. And we have adiabatic. Adiabatic means Q is equal to 0. There's no heat transfer. That means W is equal to delta E. Okay, that has some consequences as well. We're really maximizing. If we don't have any heat transfer in the theoretical way, we have a maximum amount of work that we do from the expansion of the gas. It all goes into expanding the gas. Okay. So for isothermal, then there's another one called polytropic, which just means many state. But when you do something like this, you have to find some other assumption. For isothermal, we can say work is equal to the integral of P dV. We can do this for anything, right? But we don't know, we have to get P as a function of V if it's isothermal. And so you might assume that we have ideal behavior. PV equals nRT, and we know that that is constant, so PV is a constant. P equals some constant, which is nRT over V. So then we can rewrite this as the integral of that constant nRT dV over V, and that integrates to the constant, which is nRT times the natural logarithm of V2 over V1. Okay, so that's the work for an isothermal ideal gas. They all work out like this. You always have to go back to the integral, that PdV thing. Polytropic, literally means many states, but basically it follows a relationship where P is equal to some constant times V raised to some power, negative N. And often N is the ratio of specific heats. Internal combustion engines a lot of times follow something that looks like this process. That's why we study them. But basically, you go through and you say, okay, so P times dV is work, but P is C times V to the minus N dV. Okay? So whatever the constant is, you would get that times V to the minus N over dV, or positive N, I put it in the denominator, right? Or you can leave it like this, and you can say C times, remember you raise it to the power V to the, you raise it up 1 minus N plus 1, so it's 1 minus N over that new power 1 minus N, evaluated at V2 and V1. Okay, and then you can finish that off. And often you know what the constant is, or you know what the N value is. If N is equal to 1, obviously you don't have a polytropic process. You just have PV equals PV, so it's a little bit different. But you always go back to that kind of an idea. And they work that out with some different considerations on page 168. All right, so that is going to get you pretty far through this chapter. The next part, when we get to section 4.3, we're going to talk about specific heats. So if we leave off here at the polytropic process, and I've just mentioned specific heats as being a factor, when we come back on Thursday, I can give you some more information about specific heats and the practical way of working with them. How does that sound? All right. All right. So do you guys have, at this point, do you guys have any other questions, any questions for me at all?
So test is next Tuesday, right?
Yes. Next Tuesday is my preferred time.
And then do you have like a set of questions that are going to be similar to this?
I will do that. I will give you a, let's see if I had anything here. Let's see. Oh, that's a review. That's not right. Complete list of homework problems. 2. The lecture review problems for midterm exam. Let's see what those look like. I'll just make that visible to you, and then you have 4 problems. And a lot of students really like to have that material available. Hang on a second. A lot of students like to put those on their study sheets. And I've got 2 problems here. All right, let me get rid of this. You don't need to see that, because I haven't looked at it yet, so I don't want to be giving you guys things that are not directed at what we're doing. So here's the review problems, and they're available to you. And then you'll see there's example 4-114 is the problem that I gave, and I worked that out for you right here. So you can, this is kind of really similar to what we've done today, only this is like nuts and bolts, getting down to it. So you have the review problem for chapter 4, and you also have my worked example chapter of that problem. So that'll get you where you need to go. So, yeah.
What does that part say underneath the W equals?
Oh, what? That's a constant. That's just solving for what that constant is going to look like.
And then what about right up to the right of that, those 2 words?
Right here?
No, up to the right.
You might be able to assume this is. I was saying if you have if you have an isothermal process, that means that the temperature remains the same. In order to solve this equation, you have to know what P and V, what they are functionally of each other, how they're related to each other. And I said you might assume one assumption would be ideal gas. You have to make that decision as to whether that would be a good assumption. So what I did was I just derived that equation, what work looks like for an isothermal process that is assumed to be an ideal gas. Yep, good question. I always appreciate that. I always have some students who listen very closely to what I say, and so if I leave things out, they let me know. So Isaac is that guy, so thank you. Or if I fly to it through quickly. So, any other questions? All right, so you've got the review problem for the midterm. You have a worked out review problem for chapter 4. And I will be here Thursday with any other questions. Once again, you don't have to come, but it's great to have you here, so come and we'll do some more thermodynamics. I'll talk about specific heats. It'll be a thrill. Thanks, guys.